Okay, welcome folks. Today I want to talk about quiz 4C. So this is going to be vector addition in 2D, playing around with especially like how to start a momentum problem. So this one, it wasn't immediately obvious how to do it. So I wanted to kind of show how I might start exploring such a problem, and then we'll just solve it out. There's a question. I just wondering when the session will be posted. Today is the day of obligation, so I need to make sure I watch this. But yeah, so I'll be sure to post this by the end of today. So I'm planning on posting it before 1 p.m. Okay. Cool. So we've got Kara playing fetch with her dog Jersey. You may ignore gravity for the problem. Cool. Kara throws the ball so there's initial velocity leads in plus x direction. Jersey runs and jumps in the air to catch the ball. Right before she catches it, her velocity is 12 meters per second, 60 degrees above the x-axis, as shown in the picture below. Immediately after she catches the ball in her mouth, Jersey's velocity has a direction 30 degrees above the x-axis. So they give us information about before and after the catch for Jersey. Jersey has a mass of 15 kilograms, and the ball has a mass of 5 kilograms. All right. So the first thing I want to think about, because I know it can be kind of a sticking point, is like, why can I neglect gravity? So we're on Earth, right? So there's still a gravitational force. So the only reason that I can that they're letting me know that I can neglect gravity is because whatever the process is that's happening here between Jersey and the ball is happening over a short time span. So just as a reminder, the change in momentum is given by F times delta T. So gravity is not a small f, right? It's 9.8, which in the context of this dog is not that small. But delta t is pretty small over the course of any given like short-term collision. Like the time it takes for the dog to snap its mouth around the ball is pretty short. So since delta t is relatively small, delta p due to gravity will be relatively small. That's why it's okay to neglect to ignore gravity for this problem, or why it's not going to throw off our answer too much. Okay, so part A asks, what is the final velocity of the ball? Show all work. So this is a toughie. So we have, what information do we have? Let's double check. So we have Jersey's mass. We have the ball's mass, that's good. We have a direction for Jersey's velocity, after and before. And we have a magnitude for Jersey's velocity before the collision. We don't have magnitude for the ball's velocity before or after. Okay, so when I encounter a problem where I'm not really sure what's up, it's good to just write down the things that I know. So one thing that I know is that the change in momentum for a closed system should be 0. In other words, since I can neglect gravity, there's no external forces acting on my dog plus ball system. Dog plus ball system. The total change in momentum for the two of them combined should be 0 throughout this process. So I can write that, one second, sorry, eyelash. I can write that directly as vector P of Jersey, the dog, plus vector P of the, what do I call this? The ball. Initial is the same as vector P of Jersey plus vector P of ball final. Okay, cool. All right, so starting from here, notice that this is a vector quantity. So even though it looks like it's just one equation, it's really 2. So what this tells me is that px Jersey initial plus px ball initial equals px Jersey final plus px ball initial. All right, I know my handwriting is getting a little bit harder to read, so This one, the one that starts, I'm just going to do J and B. So J is for Jersey the dog. I draw a dog. Let's try. Let's go. Okay, not terrible. More like a sheep. Okay, we've got Jersey the dog, and I'll make B for ball. So this tells me that the X component of momentum is conserved. It's also true that Py of Jersey initial plus Py of the ball initial equals Py of Jersey final plus Py of the ball final. So these are my two conservation equations. These tell me that momentum is conserved. These tell me that momentum is conserved. Questions on these two, where they came from? So all I've done here is looked for momentum conservation in 2 dimensions. So the X dimension, the X direction of momentum is conserved, and the Y direction of momentum is conserved. Okay, and the 2 points that I'm interested in are right before and after Jersey snaps the ball out of the air. So there are essentially no large external forces that cause dramatic changes in momentum. Gravity is there, but we're allowed to neglect it because the change in time associated with this grabbing the ball is relatively small. Okay, so this is what I know. I can think about this and put them into some more like, what do you say? Like concrete terms, but first let's go back and see what we want. So before I just go out and do a bunch of math, that's not very realistic. Let's try to figure out which one of these we want to chart for A. I want to know the magnitude of the final velocity of the ball. Show all work. So after the collision, I know that Jersey's velocity has a direction of 30 degrees above the x-axis. So here's the final frame. I've got Jersey. Jersey is going, here we go. Here's Jersey's velocity. It's something like 30 degrees above the x-axis. And after Jersey catches the ball is in Jersey's mouth. So the ball is going to have, here we go. The ball is going to have a velocity in the same direction. I should say V sub B. So they're going to be traveling with each other at the same speed. So they should have, in fact, the same size of velocity vector. Okay, so if I find the magnitude of Jersey's velocity, I find the magnitude of the ball's velocity. That's the insight to get. If I find V sub Jersey, I know V sub ball, the magnitude of it. Okay, and now I can think about whether I want to use the X component or the Y component to do that. So I'm just going to write out both and we'll see which one we want to select. So let's expand these 2 equations and we'll write out and we'll figure out the one that'll help us find the magnitude of VB. Okay, so since the 2 final velocities are the same, I'm just going to write both of those as V final. So if I say V final, it's either of their final velocities. Questions over here. Let's make sure that's all good. Is this okay? Why they have the same velocities after collision? This form of momentum conservation, is this all okay?
Sorry, can you explain that part, the form of momentum
So
conservation? Yeah, the 2
this one
equations.
over here?
Yeah. Mm-hmm.
Yeah, sure. So basically, if I know that the change in momentum of a closed system is 0, so delta P close equals 0, I can write that as momentum final minus momentum initial for my whole system is 0, which means that the initial momentum is just equal to the final momentum. So that's what I've written here. The initial momentum of my system, Jersey plus the ball, Jersey plus the ball, the initial momentum is equal to the final momentum for my two-body system. What I did from there is I just split this vector equation into its two parts. So how do I put this? When I add together two vectors, so A plus B, I've got two parts to that sum. I've got the x component, ax plus bx, and I've got the y component, ay plus by. So what I've done is I've split it up into its two parts. This says that, oops, I should probably change colors. This upper equation tells me that the change in momentum in the x direction is 0. The change in momentum in the x direction is 0. And I realize now I've actually got a bad subscript here. So this should be p ball final. So the right side's my final, the left side's my initial. The one that I'm going to make kind of bluish, this one tells me that momentum is conserved in my y direction. So the left side is my initial momentum for Jersey and the ball. The right side is my final momentum for Jersey and the ball. Thanks for your question. More follow-ups here? Yeah. Oops, and I should finish up. No, we're good. Okay, cool. All right. So by itself, it's not clear how to link these like kind of still sort of abstract expressions to the problem. So what I'm going to do is I'm going to try to get it in a form where there are things that I know, variables that are available in the problem. So I've got these masses, right? I've got these masses, I've got these angles, and I've got some magnitude, 12 meters per second, 60 degrees above the x-axis, yada, yada, yada. So the fact that I've got this in terms of directions up here means that I want to try to convert from my, how do you say this? From my component type representation over here to this magnitude and direction type representation. Does that make sense? So I've got some magnitudes and some directions up here. Down here, I kind of just have these components of momentum. So it's not quite linked up to the problem statement yet. So let's try that. Okay, so the x component, first of all, notice Jersey is going 60 degrees above the x-axis. She's going 12 meters a second. So we know Jersey's initial momentum perfectly. So I'm going to do the x component first. So Jersey's mass is 15 kilograms, right? Yep. So the momentum in the x direction is going to be m Jersey times vx Jersey, which is, there we go, which is m times the magnitude of velocity of Jersey times the cosine of the angle measured relative to the horizontal. All right, the second term, what's px of the ball? Well, for the ball is just moving to the right. So the x component of momentum for this ball is going to be all of its momentum. So it's just the mass of the ball times the velocity of the ball. And this is initial. So initial velocity, initial angle for Jersey, initial velocity for Jersey. Okay, so that's the left side of my x equation. Still with me? Is this all good? Too fast, too slow?
Could you explain the ball again, just in this equation? So why?
Yeah, sure. You mean this new form right here?
Yeah.
Okay, sure. Yeah. So the ball is only traveling with a horizontal component. The ball's only going to the right. So it's got no vertical component to its velocity. There's no up and down to it. So as a result, and I'm going to go ahead and lock this one moment. There we go. So as a result, since it has no vertical component to its velocity, and since momentum is just scaled velocity, the momentum in the vertical direction is also 0 for the ball. the ball only has momentum in the horizontal direction before the collision. After the collision, it's gonna have some vertical direction. But before the collision, as drawn, it's only got this horizontal component. So as a result, the momentum in the x direction for the ball is just all of its velocity. Basically, it's the magnitude of its velocity initially is its horizontal component. Does that make sense?
Wait, so why are we multiplying by cosine theta for the jersey?
Yeah.
You cut out for me when that
Sure.
was.
Yeah, no worries. So Jersey initially, is Jersey male or female? Doesn't matter. She, okay. Jersey, her velocity is going up. So there's a vertical component to Jersey's velocity. So the x component of Jersey's velocity is not the entire velocity vector. The x component is just this length, and the y component is like that. There we go. So here's Vx, here's Vy. So as a result, to find only the x component of Jersey's velocity, we need to multiply the total length by cosine of 60 degrees. And that'll knock it down to the right size of Vx in orange there. Thanks for the question. Does this still make sense? Is that all right?
Yes, thank you.
Yeah, sure thing. And I could include a cosine theta for the ball as well. So I'm going to erase this in a second, so I'm going to write it in a different color. I could write this as cosine theta for the ball initial, but theta for the ball measured relative to the positive x-axis, if you look up and to the left again, that angle is just 0. So I kind of just, if you like, skipped a step. Since cosine of 0 is 1, the momentum of the ball is just completely in the horizontal direction. Okay. Is that all right so far? Sweet. Okay, so there's our left side of the x component of momentum. Here's the right side. So the right side is going to have the same exact form, except for now I'm going to have them traveling at the same angle and with the same velocity. Okay, we've got an admin type question. Are there lecture videos for this week, lecture 6? So no lecture videos for this week, no. With the midterm last week and stuff, we're giving you a semi-break. But if you haven't seen them yet, you should check out lecture 5, which has more examples for 2D momentum. Okay, let's do the right-hand side. So the right-hand side, I've got Jersey. Jersey is now going to be, we're after collision here. So the ball and Jersey are stuck together. They're going to be traveling with the same speed and same angle of velocity. Their masses are still different. So I can write the right side as the mass of Jersey times the velocity final. I'm not going to subscript it with Jersey or ball because they're traveling at the same speed now. Times cosine of theta final for Jersey, which is, they're both traveling at the same angle now as well, because, you know, the balls in Jersey's mouth are stuck together, plus the mass of the ball times magnitude V final times cosine of theta final. Okay. So there's my x direction version. Let's also take the y component. So this kind of looks ugly. I promise it simplifies. So notice that like VF and cosine theta f are present in both of these. So at least the right-hand side gets prettier. Let's hit the y component as a magnitude direction representation. So I'm going to pull that down. Same basic deal, except for now I'm going to use sine instead of cosine because I'm still measuring my angles relative to the positive x-axis. So mj momentum or magnitude of vj times sine of theta initial. So this tells me Jersey's vertical momentum initially, plus, well, what's going to be the momentum for the ball in the vertical direction? again, the ball has no vertical component to its velocity. So the ball is going to have 0 momentum in the vertical direction. 0. That's always nice to see, right? Okay. In the y direction for the final after the collision, now they're both traveling in the same direction, and that direction is not purely horizontal. So we're going to need to keep both of these terms. So mass of Jersey times the velocity final for Jersey, which is the same as for the ball again, times cosine theta. Sorry, not cosine. I'm just on autopilot, times sine of theta, because it's the vertical component, plus the mass of the ball, v final, sine of theta final. Okay, I've got the vertical and horizontal components. Now I want one that's going to give me a handle on the final velocity of the ball. So just kind of looking at these, I have two options, right? I can either pick the top one or the bottom one. And I kind of want to think about things that I know. So the things that I know are the initial magnitude and direction of Jersey and the initial direction of the ball. That's all I have. So let's look at these two things. In order to solve this upper equation, I've got the first term on log. That's the initial momentum of Jersey, which I know. I have Jersey's mass, velocity, and angle. I don't have the initial velocity of the ball. I also don't have the final velocity of the ball. So I look at this, I say, okay, I've got an equation with two unknowns. So this upper equation is unsolvable by itself. It's unsolvable by itself. So at this point, I say, all right, it's time to look down at the other one, and hopefully this one will help me out. Otherwise, I have to solve a system of equations. That's a major bummer. So let's look at the lower one. At the lower one, I see, all right, I've got Jersey's momentum. That's fine. We know that perfectly. Then I've got Jersey's final momentum, and I've got the ball's final momentum. Okay, so at least now I've only got basically one unknown, this VF magnitude. I know Jersey's final angle, which is the same as the ball's final angle. I know, wait, hang on. Yeah, we're good. Okay. I don't involve the initial momentum or the initial velocity of the ball down here. So I'm going to use the middle one. It's an equation with one unknown, just VF. So let's solve this for VF, and then we'll finally have our answer for A. So that was the hard part. This whole thing here, finding your way in the dark, this is the hard part. From here, it's just math. From here, it's just like, you know, algebra, solving it back. Okay, so what I'm looking for is the final velocity of the ball, which is going to be the same as Jersey's final velocity. So I'm going to rewrite this equation to make it a little bit prettier, this orange equation, and then we're going to solve back for V final, the magnitude of velocity. I should probably pause for a second and ask before I go on for more questions. A lot of this was just algebra, so if you've already got a question, please do keep typing it, but I'll just say what I did recently, which is I used the momentum conservation equations in X and Y, and then I assessed which one had fewer unknowns. So, or if there was one that only had one unknown. Because the upper equation contained two things I don't know, namely the initial magnitude of the ball's velocity and the final magnitude of the ball's velocity, I decided this one wouldn't work. I looked down at the lower one. That problem is solved. I've only got one unknown, the final velocity of the ball. The initial velocity of the ball doesn't play a role in the y component because there is no y component to the ball's initial velocity. In other words, like this thing that was giving us trouble up above is just 0 down here in the y component. Okay, cool. I'm having trouble gauging if we're feeling stuck or feeling okay about this. So please do let me know if things are going poorly. Do we have the thumb down reaction? Hang on. Yeah, okay, we got thumbs up. So give me a thumbs up if you're feeling all right, Give me joy face, aka happy crying face, if you're not feeling that good about it. Thanks, folks. Okay. And we got a bunch of folks probably getting some coffee right now. That makes sense to me. It's a bit early. All right. Okay. Well, let's keep on chugging along then. Please do break in with questions as they come up. Feel free to interrupt. I'm not worried about it. Okay. Next part. So I've got this vertical part. The vertical part is what I'm going to solve because it's got this desirable characteristic of only having one unknown, namely VF. And I'm interested in finding the final velocity of the ball, which is the same as the final velocity of Jersey, the dog, because they stick together after collision. Okay, so let's solve for VF here. I'm going to rewrite my equation. This is mj magnitude vj, sine of theta 1, theta initial for Jersey, equals, and then what I'm going to do is I'm going to combine like terms. So I'm going to keep VF magnitude and sine F together, and then I'm going to just strip out the MJ and MB. So this is going to be MJ final, which is the same as initial, so I'm just going to leave it as MJ, plus MB, parentheses, magnitude VF, sine of theta F, theta final. Okay, and we're finally ready. Let's just write down the equation now for V final. I'm going to divide the left side by the right side and then swap sides. So magnitude VF, the ball and Jersey's final velocity, is going to be mass of Jersey times magnitude of Jersey's initial velocity times sine of theta initial divided by mass of Jersey plus mass of the ball times sine of the theta final. Cool. All right, let's plug in. So the mass of Jersey is 15 kilograms. The velocity of Jersey initially, I believe, was 12 meters per second. Let's double check that. Yep, 12 meters per second at 60 degrees above the x-axis initially, 30 degrees finally. So the initial angle for Jersey is 60 degrees, sine of 60 degrees. Sweet. Also, this is a small dog catching a really big ball. Whoa. All right. So the masses of the two. So we've got a 15 kilogram dog and a 5 kilogram ball. 15 plus 5 down here times sine of 30 degrees. So 60 for the initial angle, 30 for the final angle. All right. And if I try to run that calculation, let's see if I can make too many typos in my calculator. 15 times 12 times sine of 60 is 155.8 on top. 155 point, that's supposed to be 5, so S's. All right, 155.88 on top. And on the bottom, I got 20 sine 30, which is 10. So I've got a final velocity magnitude of around 15.6 meters per second. If anybody happens to have the solution up, let me know if that looks good to you. But I feel okay about it, reasonably confident.
So I was like cut out for a bit. Where exactly did sine 30 come from?
Can you say again, Jordan?
Where did sine 30?
Where did sine 30 come from? Is that a question?
Yeah.
Okay, cool. So the sine 30 came from the fact that that is our final direction that we know Jordan's going in relative to the x-axis. So this is before and after the collision. Before the collision, Jersey is moving 12 meters per second at an angle of 60 degrees above the x-axis. That's where the sine 60 came from. And then after the collision, when the two are stuck together, Jersey's velocity is 30 degrees above the x-axis. So because Jersey and the ball are stuck together, they share the same direction and magnitude of velocity. They share the same velocity vector. So the 30 degrees came from, here we go, the right-hand side of the equation. in this upper part when we're solving the initial and final y components of the momentum. So yeah, does that work all right? Does that make sense? Jordan?
Yeah, sorry, I just didn't see the 30 degrees in the
Oh,
initial.
in the problem statement? Yeah, no worries. No worries. Cool. All right, 15.6 meters per second. Okay, so we've done all this backlog of work already to find all these little more theoretical type expressions. So we're finally ready now to find the initial velocity of the ball. So recall that when we looked at our expressions, let's box them so it's clear what I'm looking at. When we looked at the expressions for momentum in the x direction, momentum conservation in the x direction, and momentum conservation in the y direction, the problem that we ran into with the x direction was that we didn't know the initial velocity of the ball. So since we didn't know the initial velocity of the ball, or sorry, since we didn't know the initial velocity of the ball, and we also didn't know the final velocity of the two, we couldn't solve for anything. It was two unknowns. Now we know the final velocity of the ball from our second equation, and we can just solve back using that knowledge to find the initial velocity of the ball. Sweet. Cool. So I'm going to use the x component for the second part. Sound good to everybody? Okay, so for this second part, I'm finding the initial velocity of the ball, the initial of the ball. And let's do that. Okay, so again, I'm just going to make this equation a little bit prettier. So first thing is, I can't do anything on my left-hand side. We're just stuck as is. MJ VJ initial times cosine, oops, I should put magnitude bars, times cosine of theta initial for Jersey, plus m of the ball, mass of the ball, times the initial velocity of the ball. And again, no angle here because the ball only has a horizontal component, equals, I can again combine like terms, so mj plus mb, then magnitude v final, which we know the value of now, cosine theta final. Sweet. All right. Rearranging for v initial, what do I get? So this is for v initial of the ball. There we go, v initial of the ball. This is the thing that I'm solving for. So I'm going to subtract this first term on the left-hand side and divide the whole thing by mb. And what that's going to give me is, let's do a rare choice of color that is actually same. So the magnitude of initial velocity of the ball is just the right-hand side minus this first part of the left-hand side over mb again. So mj plus mb vf cosine theta f minus mj magnitude v Jersey initial cosine theta initial. Sweet. All right, then I divide both sides by mb. So over mb and over mb. All right. And cool. So again, this was relatively quick to do now that we've got our system of equations up here for momentum. So what I want to do from here now is just plug in. That's all I have to do. Questions on what I did to rearrange or anything here for the x component of momentum?
Would it be wrong to have like the entire, like each separate entire equation over MB instead of just the MJ and MB?
You mean like if I did this and then divided that by MB?
And like each one was separate, like so it would be like MJ plus MB VF cosine over MB minus MJM VJ VJ initial cosine over MB.
So are you thinking something like this? If I did over MB versus over MB? Or are you saying
Well,
like, go ahead.
like Also including the MJ and MB like on top of it. So like that, yeah.
Yeah, that's equivalent. Yep, you're good. That's the same
Okay.
thing. No worries. Yep. And that's just because if I have like a if I have a fraction a over b and I multiply it by another number c, that's the same as c times a over b. Multiplication can distribute inside of parentheses. Yep.
Okay.
Good stuff. Thanks, Jordan. All good. And I could also just divide the whole thing by a single MB too. In practice, this is probably how I would write it on a test, just because I'm moving fast, you know. Yeah. Okay. Final over MB and over MB. All right, let's plug in. So MJ plus MB, that's 15 plus 5 kilograms. The ball's mass is 5. The final velocity we calculated before is 15.6 meters per second. And the final angle is 30 degrees. So this is cosine of 30 degrees. Minus MJ over MB, that's 15 over 5. Again, it's not a big enough dog to catch this ball. Times, so the initial velocity of Jersey, which is 12 meters per second, that's given in the problem statement, times cosine of 60 degrees, the initial angle with which Jersey leaves the ground, or with which Jersey catches the ball. Okay, and yeah, let's plug in. So 20 over 5 is 4. 4 times 15.6 times cosine of 30 gives me 54. Hello. 0.04. Probably that's neglectable, but who knows? Okay, kilogram meters per second in the y direction. Cool. Wait, it's just going to be meters per second. Sorry, not thinking enough about my units. Meters per second minus 15 over 5 times 12 cosine 60. So that's going to be 3 times 12 times cosine of 60, which is 18. So 54 minus 18 is just 36. Equals 36 meters per second. It's a pretty fast moving ball. The dog, that's skill for the dog. Okay, so 36 meters per second. Wow, it's so fast. All right, 36 meters per second. Let's write it down. So parts A and B here are kind of combined. I needed to solve this system of two equations in order to find the answer. And there's no way that I could have known off the bat, like without having practiced any similar question or anything like that. There's no way I could have known off the bat that the y component was going to be easier to solve. Now we can hopefully carry forward the intuition that if one of our systems only has one component, that component will be the harder one to solve. Yeah. So like here, because one of our two subsystems, the dog and the ball, didn't have a vertical component, the vertical component was actually the easier of the two to solve. That's a good kind of like general idea about momentum conservation to carry forward. Okay, hopefully that pacing was okay. I know we're all coming at it from different like levels of experience with momentum. There we go. Sorry, this should be the initial of the ball. Why did I say the final? I'd love to take a couple more questions here. If not, no big deal. I'm down to go down to the momentum chart. Just as a general thing, can I get some more thumbs and crying happy joy faces? So thumbs if you're all right with it, crying with joy if you're like, no thanks, dude. I did not love that. Okay. All right, moderate results. Okay, so as an overarching summary for A and B, what did I do? I wrote down the rule for momentum conservation. So for step one, I wrote down the rule for momentum. I mean, this is not like a cut and paste type, here's what you should do, but just to let you know what I did for this one. I wrote down my rule for momentum conservation. I split it into its parts, x and y. I subbed into those parts things that I put it in a form that made the information in the problem useful. So in this case, I subbed in masses and velocities and angles. Then what I did is I assessed those two equations, my two equations for x and y and momentum. And I said, okay, which one of these is actually solvable? Which one only has one unknown? If it's two equations and two unknowns, I could also manipulate them using like system of equations stuff to solve them, but that's a bummer. So I'm going to try to avoid that. So what I did was I tried to find one that only had one equation and one unknown. It turned out to be the y component. And then by solving the y component for the final velocity of the ball, I was able to go back and solve the x component for the initial velocity of the ball. So actually answering A and B came at the very end of that process. So yeah, so it helps to explore a little bit, with the math, see what you can solve and what you can't solve. Okay. And there's my super quick summary of A and B. So let's look at C for a moment. I've got this 2D momentum chart for Jersey catching the ball. I'm supposed to go ahead and draw in each of the vectors, and I might as well include their magnitude and direction now because I can. So before I do fill out this momentum chart, do we have any more questions about my summary or anything like this? Okay. Let's hit the momentum chart then. So I know the initial and final velocities of everybody now. So that's kind of nice. So Jersey, I know first. Jersey has a magnitude of velocity of 12 meters per second. So Jersey's momentum, let's calculate it. Jersey momentum, Pj, is going to be the mass of Jersey times the velocity of Jersey. Jersey's velocity vector is initially oriented, here we go. Initially oriented 60 degrees above the horizontal. So whatever I draw in for Jersey here, her momentum vector, it should also be oriented 60 degrees up from the horizontal. The magnitude of this momentum, magnitude Pj, initial, is just going to be the mass of Jersey times the magnitude of the velocity of Jersey. So I know the magnitude and the mass, so that's the easiest thing to see. Her mass is 15 kilograms and her initial velocity is 12 meters per second. So 15 times 12, I feel like that should be something I know off the top of my head, but I don't. It's 180. There we go. So the magnitude of initial momentum is 180 kilogram meters per second. Kilogram meters per second. There we go. So Jersey's initial momentum points up 60 degrees. 60 degrees, there we go. And it has length 180. I'm going to put the length of the vector in the top left corner. 180. Okay, now for the ball. The ball has an initial velocity of 36 meters per second, and it's traveling purely horizontally. So similarly, I'm going to calculate P ball as the mass of the ball equals, mass of the ball times the velocity of the ball. So the velocity of the ball in component form is just going to be 36,0. Why is that? Well, it's only got a horizontal component and the magnitude of it is 36. So it's going to be 36,0. So the momentum of the ball is going to be given by 5 times 36, the magnitude of it, which is also 180. Whoa, that's crazy, man. Okay, so it's also 180 and it's pointing to the right. $180. Sweet. So these two vectors should have the exact same length. One sec. We got some serious glare going on over here. All right. So questions about these first two momenta, the initial momenta. Okay. Hanging out, it's all right. Okay. So the total is going to be the sum of these two things. In order to like perfectly find these two vectors, I would need to add them up component-wise. So in particular, the x component of Jersey's momentum is 180 cosine 60, and the x component of the ball is 180, just 180 flat. So the x component for the total momentum, P total initial, x, P total initial y. The total initial momentum in the x direction is Jersey's momentum in the x direction. So 180 cosine of 60 plus the ball's momentum in the x direction, which is 180. And the y component is going to be 180 sine of 60. Only the ball, or only Jersey contributes. So 180 cosine 60 plus 180 is 270. Should have seen that one coming. So 270 in the x direction. And 180 sine of 60 is, I don't remember my unit circle. I'm too stubborn. All right, 155.8. So 156. Okay, kilogram meters per second for both of these. So the sum of the ball and Jersey momenta is going to be a vector that mostly points to the right and a little bit up, or about halfway as far up. So something like, let's keep our coloring consistent here. There we go. Something like this. Whoa. Oh no, I've made my chart too small. I can see. There we go. Something like that. Okay. And with foresight, I should have probably drawn these other vectors a little smaller, but it's too late now. So this is the magnitude of this thing is going to be 156 squared plus 270 squared square rooted. (270 squared square rooted). So that's 311. So it has length 311. And the angle it makes with the horizontal, I can find using tangent of an angle is opposite over adjacent, or in other words, py over px. All right, so that angle, if I do an inverse tangent, arc or inverse tangent on y over x, I get 156 over 270, which is 30 degrees. So this makes a 30-degree angle. Okay, so again, I'm just kind of flexing my conversion between the component form and the magnitude and direction form. So the component form is what I need to add the vectors, and the magnitude and direction form is often the way that I'd like to express a vector to make it a little more visual. So I know roughly what 45 degrees above the horizontal looks like. I don't really know what the vector 5, 5 looks like without thinking about it a little. Okay, questions on this first column? Is that all right? Okay, the first column is actually the hardest. That's nice. So delta P for my total system is going to be 0 because it's a closed system. So I can fill in that one easy. 0. Delta P is a little bit harder to think about unless I know something directly about the forces. So I could fill in delta P right away if I knew F delta T for either of these objects. However, I don't. I do have a handle on the final momenta of each because I've got final velocities and final angles. So let's do that. The final velocity of the ball is 15.6 meters per second, and it's directed up 30 degrees. 30 degrees, there we go. So the ball's final momentum is going to be, I mean, the same as we did. We'll use the same kind of calculation scheme we did for the initial. So I'm going to multiply the magnitude of the velocity by the ball's mass. That'll give me the magnitude of momentum. And I know it's angled 30 degrees above the horizontal. So 15.6 for that final velocity of the ball times 5 kilograms for the mass of the ball. That gives me 78. It has a length of 78, which is a bit shorter than it was before. This should be for the ball, my bad. 78. And it is angled 30 degrees above the horizontal. So 78 for the length. So the ball's momentum has decreased in magnitude. Decreased in magnitude. The velocity of the jersey, the velocity of jersey is the same, 15.6, but her mass is 3 times as big. It's 15. So 15.6 times 15 gives me a length of 234. And again, that angle is just 30 degrees above the horizontal as given in the problem. So here goes the long vector. Whoa, 234. 2, 3, 4. Cool. All right. So my total momentum, the momentum of the entire system, fortunately, like it's kind of nice. These two things align with each other. They're both angled at 30 degrees. So when I sum up these two vectors, I don't actually have to break them into components if I don't want to, because they're both pointing the same way. So their lengths will just add completely. 78 plus 234. If you want, like if that's not comfortable, if you're more comfortable always breaking it down into components, you can do that. This is just kind of a shortcut. If two vectors point in the same direction, then their magnitudes actually do add. If they point in anything other than the same direction, their magnitudes won't add. But here we are. We might as well use the knowledge. 234 plus 78. 312. That's weird. I picked up an extra 1. So that's too bad. Let's look at that in a second. Hang on. Okay, so first of all, I need to redraw a few things. I'm going to make this upper vector a bit smaller. Not quite perfectly drawn to scale here. Okay, something like that. There we go. So this vector should stay the same size. Good. Okay, nice. That's much better. Okay, so 312 here. The reason I shortened this vector was because I realized that 234, a length of 234, looked like it was longer than 311, and that can't be, right? So that's why I shortened this upper vector. Now, the reason I said that I picked up an extra 1 somewhere is because we should be able to add horizontally too, and not just vertically. So your expectation should be that the vector on the left should be the same as the vector on the right when the change of momentum is 0. I picked up an extra 1 somewhere along the way, probably due to rounding. So 311 and 312. No big deal. If it was a quiz, I would probably go ahead and correct myself here and just say 311. Yeah. So I'm within 0.3%. It's pretty darn close. Okay, and the last thing to find is delta P. So P final minus P initial. Delta P equals P final minus P initial. And if I want to be precise about it, what I should do is definitely break it into components and subtract here. We've got a minute. Let's do this, and then we'll call it a day. So I'll do it in terms of actual components, just to be very precise. Doing it kind of visually here, I can tell that the vertical component of Jersey is going to decrease. So my guess for delta P, just looking at it, adding head to tail like this, is that delta P should point down to the right, something like that, for Jersey. And for the ball, it's going to point left and up. So again, what I'm doing is I'm kind of doing like a mental head to tail addition of these vectors. So P final minus P initial. Oops, I should probably make it a little bit more reasonable. There we go, something like that. Okay. So that's my general guess for how big they should look, just doing head to tail addition. If I want to be precise about it, I do P final minus P initial component wise. So let's break it into components. I'm going to be a little bit sloppy with notation here, but I'm doing the X component up top and the Y component on the bottom. So the X component on top is 234 sine 30 minus 234 sine 180, or sorry, cosine. 234 cosine 30 minus 234 180. Cosine 30 minus 234, not 234, 180 cosine 60. Holy cow. I think I just misused all of my words. Let me write it. I'll write it once. And then after that, I'll just solve it real quick. So 234 cosine of 30. 30, there we go, that's a 3, 0. Minus 180 cosine of 60. Hello. Fort Pierce, Florida. Nice. Telemarketer, probably. 234 cosine 30 minus 180 cosine 60. That's 112. So 112 in the x direction, positive 112 in the x direction. In the y direction, well, that's going to be 234 sine of 30. 234 sine of 30 minus 180 sine of 60. That's the two y components for the first one. That's negative 38. So it has components that are 112 by negative 38 for this first one. Similarly for the second one, I'm not going to show it because we're over time, but it'll be the opposite. So it'll be negative 112 comma 38, which will sum to 0. So the thing about momentum charges is that they should sum appropriately both left to right and up to down. So anytime I'm wanting to check my answers, I can do just a bunch of little quick mini head to tail additions. The middle column, these two vectors sum to 0. The left column, these two vectors sum to form a vector that's up and to the right. This one, same deal, up and to the right, and then left and right, they also add. Okay. I think that's it for now. Any quick wrap-up questions before I end the recording? Thanks, folks. I know this one, all of these momentum questions are kind of a slog. There's lots of computation to do. So I always try to bring it back to the concepts and procedures. Thanks, y'all. Catch you later. I'll go ahead and end the recording just in case there's anything we want to talk about.